Okay, good morning. This is alternating series, more tests, day number 5 on conditional convergence, as well as power series. Today, because we are going to do some Mall of America preparation, all that we're going to talk about is absolute convergence. We're going to save power series and the rest for tomorrow and the day after. So absolute convergence, how shall I describe the... let's look at two series. I want to show you a counterexample of absolute convergence. Let's go from n equals 1 to infinity of -1 to the n over n. All right, let's look at those terms. That would be +1 minus a half plus a third minus a fourth plus a fifth, da-da-da-da-da, down the line. Is that alternating series convergent? Well, we have to determine that in two ways. Right? The first way is to show that the b sub n plus 1 term is less than b sub n. Let's do that first. I want to show that this is convergent. So let's take, would it be -1? Yeah, it would be. Let's add a +1 here so I don't have to change everything. That would be a +1. Good. Okay, so let's show that sequence, b sub n, would be decreasing. Okay, so what is b sub n? No, because the first one would be positive, right? So I just changed that to a +1, so it changes all the signs back to what I want it to be. Okay, so what is b sub n? Somebody hollered out. 1 over n, right? Take the alternator out, it's 1 over n. So b sub n equals 1 over n. I want to show that 1 over n plus 1, although very straightforward, and you could probably look at it and say clearly 1 over n plus 1 is less than 1 over n. You actually have to prove it. So you're going to do this, 1 over n plus 1 minus 1 over n. How do I show that that'll be less than 0? Well, I have to get a common denominator. No, plugging in numbers doesn't work that way. So I'm going to get a common denominator. So I'll have n minus, what would I get on the right side? I'd have to multiply that by n plus 1. This is fairly straightforward, right? So I'm going to distribute the negative to both of those. So that would be a negative n minus 1. So what am I going to get here? Oops, sorry. What's n minus n? 0. That goes away, and then I get a -1. So I get -1 over n, n squared plus n, or n times the quantity n plus 1. That will always be less than 0, clearly, because the numerator is negative and the denominator will always be positive. Okay, so check. We can say part 1 that b sub n plus 1 is less than b sub n, therefore b sub n is decreasing for all n values. Second thing we have to do is show that the limit as n goes to infinity of b sub n equals 0. Well, that's clear. Done, right? So we've shown that this alternating series is convergent. So the sum from n equals 1 to infinity of -1 to the n plus 1 over n converges by what test? The alternating series test. Okay, by the alternating series test. Let's pause for a moment. I'll let the kids on the web catch. If I were to take the absolute value of this series, what could I call it? Yeah, b sub n, right? If I take the absolute value of the alternating series, I get b sub n. Now, we need to show, let's see if this converges. How would we test that? Because I know that the limit as n goes to infinity of this thing is 0, but all that means is that it might converge, right? Then we have to do a test on it. What test should we use? You could use the ratio test if you want. You want to use the ratio test? We could do the integral test or the ratio test. Ratio test, okay. All right, let's do the ratio test. Say again. If the ratio test equals 1, what are we going to do after that? Integral test. So should we just jump to the integral test? I don't know, does it? Let's test it. Let's do the ratio test. Let's do the ratio test. So it would be 1 over n plus 1 over 1 over n, which will be n over n plus 1, which will be 1. So the ratio test will say inconclusive. So why don't we just jump to the integral test? Let's go to the integral test. So that tells us that from, good morning, from 1 to infinity of 1 over n dn, if that comes out to be a, thank you, he actually just left for a moment, but I'll give it to him when he gets back. If that comes out to be a finite number, then we know that this sequence or this series will converge. Let's see what it is. What's the integral of 1 over n dn? Natural log of n from 1 to infinity. Oh, we have to do some improper integration here. So that will be the natural log of infinity minus the natural log of 1, and therefore that will be infinity. Therefore, what happens to this series? It's divergent. Okay, so here we get to the concept of the day. A series is absolutely convergent if its alternating series and the absolute value of its alternating series both converge. Therefore, this function right here, or this series right here, is not absolutely convergent. It is conditionally convergent. So there's two types. There's two types. One, which we just did, is conditional convergence. This is conditionally convergent. All right, the second is absolute convergence. And we can get to an example of that in a moment if you want. So if both of them had come out to be convergent, it would be absolutely convergent. Since only one of them did, it would be conditionally convergent. Now here's the cool thing. If you test the absolute value of the alternating series first, and it's convergent, the alternating series of that will also be convergent. So you always want to test the absolute value series first. If it converges, then you know both do. If it doesn't, then you want to test the alternating series to see if it's conditionally convergent or not, because it's possible that both could be divergent. Let's pause there for a moment. Gross. Yeah, go ahead. That's cool. Fine, she says. Straighten it out. I wish I had the IKEA gains. So good. So good.